5.1 antiderivatives. So what we're going to do now is the other half of calculus. We do derivatives and we're leading into integrals. And what we're going to start with is antiderivatives. We're working backwards. So we know, for example, that if we were given f of x equaled x, and we could take its derivative, which would be 1. So to work backwards, it's saying we would be given f of x is 1, and we want to find its antiderivative, and I'm going to denote it with a capital F of x. And going backwards, its antiderivative would be x for f of x equals 1. So we're working backwards. So let's do another one here. If we're given that f of x is equal to 2x, working backwards, we know then that its antiderivative would be x squared. So in this case, if we were to take this antiderivative and take the derivative of it, so the derivative of x squared would be 2x. Well, notice then that leads us back to f of x. So that's the key concept here in the definition of the antiderivative, is that the function with the capital F is the antiderivative of function f on an interval, provided that the derivative of the antiderivative gets you back to the original function. So it's just kind of going backwards and then checking your work that you did it correctly by taking the derivative. So I'm going to go ahead and get a little ahead of myself here, and I'm going to go ahead and say something about doing power rule. I did f of x with the x squared here, but what if I had that f of x was 3x squared? We kind of know what it should be because of being able to take the derivative easily. But remember with the power rule that we would always bring the exponent down as a multiplication factor and subtract 1 from the exponents. So I'm going to go backwards in this process. I'm going to add 1 to the exponent. So I'm going to show you here that I'm going to say it's really add 1 to the exponent. Instead of multiply, I'm going to divide by that new exponent. So then this would simplify down into x cubed. So we did walk backwards, and if I take the derivative of x cubed, I should get back to my original f of x, 3x squared. So going on to this concept, we're going to be talking about the family of antiderivatives. Let f be any antiderivative of the function f on an interval. Then all of the antiderivatives of this function on the interval have the form of capital F plus c, where c is just any number. Because constants, the c's, the derivative of it would be 0. So it could be any c. So for example, I could be given f of x equals x squared plus 3, and if we took the derivative of it, we get 2x. If I had, for example, this function, x squared plus 5, the derivative, because of that constant, would be 2x. And then if I did another one more, x squared minus 8, taking this derivative, we get 2x. So the only difference that we see all the derivatives of these three functions are the same. The only difference from the original functions was the constant. So if we're going to do these antiderivatives, we don't know what the constant was, if there even was one. So we're always going to have that plus c. So the other thing is, if we can do this by graphing it, and we could see that if I had let's start with that. The antiderivative is x squared plus c. Then I can see if it was c is 0. If c was 2. We could do one We're the f of x and then minus 1. So this is the family depending on what the constant's going to be. So we can remember when we start working through some of these examples, you can always take the derivative to check your work. So let's start with example 11. We want to find the antiderivative. And we can't forget the c because of the family of derivatives. We're going to go ahead and do number 13, which is f of x is equal to the sine 2x. So this is another thing we haven't really talked about yet, but we haven't talked about chain rule. This is like doing the anti-chain rule in a sense. We got to do, instead of multiplying by the derivative on the inside, we're going to divide. So we're going to go ahead and for this one, we know the anti of sine x would be cosine 2x, but there's more to it than that. It turns out if I was to take the derivative of cosine, it should be negative sine of 2x. But there isn't a negative in my original f of x. So I have to say, well, negative. So now if I take the derivative of a negative cosine 2x, I would then get a negative of negative sine x be positive. So that's something we're going to come back to in a minute. But I have plus c, but I have to deal with this chain rule. So instead of multiplying by the derivative of 2x, I'm going to divide. So the derivative of 2x would be 2, so I'm going to divide by 2. So this would be my answer for number 13. All right. E of x, which is one of our best ones we can do. Number 19, we have the function f of x is equal to e to the x. Its antiderivative is e to the x. The only thing we have to remember is the family of antiderivatives. So that's our answer to that one. Okay, so from here, I want to go ahead and I want to talk about the power rule. So this is what we were talking about for what I said, the shortcut. We're going in opposite directions. Add 1 to the exponent, divide by the new exponent. But for the definition, the theorem that it's going to give to us, there's something else we have to talk about first. We're going to use the integral sign. This is the integral. And then we're going to have some function f of x dx. So we're going to say this is the integral. Oops. This is the integrand. And technically it should add this, but this we're going to hold off until another section and we're going to talk about it. But we're going to just remember that this is the variable of integration. For now, that's what we're going to say. So the biggest thing is we talked about the process if we were using, so that we're going to use this integral, like for example, the integral of x dx, the integral of x squared dx, and the integral of x cubed dx. These are all three different ones. We're going to find the antiderivative of them. So remember, we're going to add 1 to the exponent, divide by that exponent, plus the family. This is indefinite. So we're going to do add 1 to the exponent, divide by the new exponent, add the family. Add 1 to the exponent, divide by that exponent, add the family. So we're going to go ahead and use this now notation, and we call this the power rule for indefinite integrals. Indefinite because we could do an infinite number of families of this function depending on what c would be. So I have this power rule. It does write out about adding 1 to the exponent and dividing by that new exponent and adding c. Just remember, p cannot be -1 so that we can keep this real. All right, so let's go to some examples. I'm going to do number 28. And I'm sorry. Before I get into examples, I want to do the constant multiple and sum rules. So constant multiple, remember even with the derivative, if it's being the function's being multiplied by something, it's still there. I do the derivative to the function, and then I can, at the end, finish multiplying by that constant. So the constant multiple rules with using the integral sign is you can pull out as a multiplication factor from the sign. It's always going to be there. So we got to remember that. The sum rule is that if we're given two different functions, adding or subtracting, we could separate them and take the integral of both functions. Same thing that we had when taking the derivatives. So now let's get into some examples. I'm going to do number 23. So for number 23, should be easy. Notice though, that you should, in proper notation, if you have more than one term, or more than one function in this case, you really should have it in parentheses times the dx, the delta x, the change in x. We're going to come back to y in a little bit, but some people write it without, and it's technically wrong. So this is the correct way to do this notation. If we're going to do the antiderivative of this first term, remember, we're going to add 1 to the exponent, divide by the new exponent. And then I have minus. We're going to go ahead and add 1 to the exponent, divide by the new exponent, and then plus c. The last thing we would need to do is then simplify this and see that we have this expression, and that's our antiderivative. Okay. The next one I want to do is number 28, and this then will help us get a little bit into a constant rule, and we haven't learned anything else, so we need to make sure it's in a form that we easily can take the antiderivative of. So there's two ways we can do this. We can leave the 5 in there and multiply it through, or we can factor out the 5 as a constant multiple and then simplify the inside. So I'm going to go ahead and do that way only for our example. I'm going to have the constant, and then I'm going to go ahead and distribute m to both terms. I have 12m to the 4th minus 10m squared in parentheses dm. And then from here, I can take the antiderivative. So I'll have 12m to the 4th, adding 1x to the exponent, so to the 5th, divide by the new exponent. Minus 10m, add 1 to the exponent, divide by the new exponent. Plus, c at the end. I'm not multiplying 5 to the c. In a sense, it just creates another constant, so it would still be c technically. So I'm just not going to bother with it there. I'm going to multiply this in, so I have that 5 here reduces and that 5 here, so that I really have 12m to the 5th minus 50 thirds m cubed plus c, and that's our antiderivative. So you could have left the 5 in and worked from there. We do have some trig functions, and I want to go ahead, there is one more I wanted to do dealing with a rational exponent. So let's do number 30 before we move to trig. This is technically one term, it's not in parentheses, but I have a constant that I can pull out as a constant multiple. And then instead of writing the cube root of x, I'm going to put it in exponential form. And then from here, I can go ahead and take the derivative. So I'm going to add 1 to the exponent, which would make this 4 thirds, divide by the new exponent, and then add c. Simplifying this, I get 6 times, and I'm going to do the reciprocal, And simplifying it further, I get 9 halves x to the 4 thirds plus c is our answer. This one will not be in the homework, but I wanted to make sure that we went over that one. So I'm going to go ahead and I wanted to do at least one trig, and then we can move on. So from here, let's do number 46. It's technically one term, so I'm going to go ahead and do my antiderivative. The antiderivative of cosecant squared should be cotangent, but normally the derivative of cotangent is negative, and cosecant here, squared, is not negative. So that means I need a negative cotangent of 6x, and then I'm going to divide by the chain rule, and then I have to add my family of antiderivatives. So my answer for this one is here. So it's a lot more to think about as far as just taking the antiderivative when it comes to the trig, and because it's had not just a simple x in the function. So I want to go ahead and show you two lists that are in your book, infinite integrals of trigonometric functions. So it shows you then here on this column, if you're taking the antiderivative, what it should look like as far as even with the chain rule, in anti-chain rule. And then I also have another list of indefinite integrals dealing with e, exponential, log, and inverse trig. So those are the ones I could walk through them, but it'd be just easiest if you use your lists when doing the homework. So let's go ahead, and from there, let's do an example of 52. All right. This is one expression, so it's not in parentheses. But if I go to do this, I could pull that 2 out. I don't have to. And then it's just a little easier to see that what form it's in. And we can see that it's in a form where if in our list, that I'm going to tell you what page it's on too. This is in your book on page 343. That if I see that it's going to look like the antiderivative, and it's going to have the dx here because the 1 is in the numerator, and it looks like should be tangent. So it says here it has dx over a squared plus x squared. This could be rewritten into that form. We can do that. But we know that it switches, and then it says here the derivative, the antiderivative of that would be 1 over a tangent inverse of the x over a plus c. So this becomes a lot easier to do this. You can see that the problem is what do I do here as far as the 25? Is squared. This is squared. So what is my a is really what I'm asking. So my a in this case should be 5. Okay, so from there, the only problem is I have something else with the 16. So it's not as simple as 5. Maybe I could do this. How about, I'm not going to say that. I'm going to go ahead and manipulate this by multiplying this by 1 over 25 over 1 over 25. And if that's it, I have to pull this out. Well, it's there. Let's leave it. Let's see if that's it. If that's the case, let me rewrite it one more time. If I distributed that 1 over 25 to the numerator and the denominator, I now have this. I'm a lot closer to what it looks like I should be. But in this case, then, I really need to factor out that 1 over 25 again. So I'm going to do that. my goodness. I think I just did that backwards. Nope, that still works. All right, so I lost my DZs here. All right, so from here, I'm going to take the antiderivative, and it should be the tan inverse of 4 over 5 plus c. But then I've got to do the antiderivative of the chain rule. So hold on, let me keep going here on this one. This might be easier to see this form. That's where I got the 4/5. But I've got to go ahead and divide this by the inside because that's not just x. Oops, z. I got to go ahead and say 2/25 divided by 4/5 tan inverse of 4/5 z plus c. And then I'm going to go ahead and simplify this even further. And I see that it should end up being 1/10 tangent inverse of 4/5 z plus c. And that's our final answer. So the thing is, even with the formula, it's still a little bit more trickier when we have other constants or coefficients in there. So that would be where I'm going to stop at this video.